I'm going live. Meeting's being live streamed. All right, so let's go check on it then. Okay, I think we're finally live. So now what I need to do is get my apps ready. All right, that's ready, and then share my screen. Cool. We're gonna share the screen. All right, here we are. Very cool. And let me stop sharing my screen and make sure that the live stream is still good. Really no way for me to check, huh? Okay. Then I will just leave that open and hope it works. Yeesh. Amateur hour. All right, we're good now. All tests are done. Share screen. And we're just gonna have to trust that the presentation is on the screen because apparently I cannot check. Actually, no. I can check from my phone. That's probably smarter. All right. Those of you who are joining us, we are setting up for a Digital Inclusion Week talk. This is going to be our first of 6 different presentations throughout the week. Oh, jeez. I can hear the live stream, but I don't see it. All right, here we go. We're good. Sweet. All right, so it is sharing my screen. Awesome. I'm just going to go ahead and full screen this and we'll get started. Whoa. So like I was saying, my name is Anthony Hake. I'm the Director of IT for Oak Hill Collaborative, and we're celebrating Digital Inclusion Week 2022 in style. We have 6 different presentations and workshops lined up for you this week. Starting with this one, we're going to do a very simple robotics exercise. We are going to take the Raspberry Pi microcontroller and we are going to program the temperature sensor that is on the board. Other talks this week include tomorrow there's going to be a resume workshop. So if you want to kind of brush off your Microsoft Word skills or sharpen up your resume, that's tomorrow at 4. Tuesday, we're going to be going over what was it? Smart cities? No, I think we're gonna have Steve Kristen from Eastgate, Council of Governments. He's going to talk about what makes a smart city so smart. That's going to be at noon, by the way. Following that, we are going to have another robotics workshop. This one a little bit more in depth, provided by Cameron Hughes from C-Test Labs. That's going to be Wednesday at 6 p.m. Thursday, we are going to have a very special guest, Wes Stanton from Amazon. Yeah, that Amazon, the one on the app that's installed on your phone. And he's going to be doing a very interesting talk about how the same exploits that professional gamers use to speed run games are similar to the exploits that are used to dismantle the security on an information system, for example. And finally, we're going to end Digital Inclusion Week 2022 with a returning guest. Excuse me if I butcher this. Kaneko Himari is going to be presenting virtually how they do streaming with their digital avatar. It's called VTubing, or being a virtual YouTuber. They would know a lot more about that than I do. So if you're interested in that in the slightest, that's going to be our last workshop for the week, Friday at 6 p.m. But enough about that. Let's talk robotics. Robotics on a tiny scale. I was going to rig up a camera so that you could actually see me plug in the Raspberry Pi Pico and handle it. But if you're following along, I feel like that step doesn't require visual aid. That and because I only have one screen, it's a bit difficult for me to keep track of everything that's being streamed all at once. So to keep things simple, we're just going to assume that you're either listening in, or that if you're following along, you're able to follow very simple instructions such as plug in the cable, things like that. If you have any questions about this talk, there will be a live discussion Q&A at the end. If you are watching this live stream after it's already come and gone and is now archived as a video, you can reach me at anthony@oakhillcollaborative.org. But without further ado, let's get right into it. This is Digital Inclusion Week Day 1, Robotics on a Tiny Scale. And that right there is actually what the Raspberry Pi Pico looks like. It's a microcontroller from the Raspberry Pi Foundation. I actually have one right next to me. So what are we going to discuss? We are going to discuss approaching robotics from a simple level, because I think one of the most intimidating things about robotics is everyone assumes that they have to be a rocket scientist or a computer scientist to be able to comprehend what's going on here. And I'm here to say that while robotics is complex, it's not impossible to understand if you break it down into smaller chunks. And we're going to talk about what those chunks are. We're going to talk about the difference between microcontrollers and sensors and why they are so relevant in robotics. We're actually going to be programming our Raspberry Pi Pico during the presentation, and I'm going to show you the script that I use to enable the temperature sensor that is built into the board. And it's actually it's the same temperature sensor that tells the Raspberry Pico that it's overheating. We can actually utilize that sensor to tell us how hot it is in the room. And we're also going to go over troubleshooting and debugging. That is really just time for me to fix my code if for any reason it doesn't work. And I'm sure that is a process that you may want to see as I go along. And assuming I get it right on the first try, by all means, we will do something else during that time. Maybe convert the temperature from Celsius to Fahrenheit. Who knows? And then we're going to wrap up with some commonly asked questions, and that will be time for those in live chat to forward their questions for me to answer on stream. And yep, that's it. That's all we're going over today. So without further ado, we're on to approaching robotics from a simple level. When you look at that robot on the right there, it is obviously very complex. There's a lot of different sub-assemblies that work together to ensure that the overall goal of that robot is met. This is a collection of motors, a collection of sensors, and microcontrollers that are working in tandem with a central processor to keep them all in line. So to make robotics a bit more simpler to understand, we're going to look at one of these systems, the system on the microcontroller that tells it that it's overheating, for example. This may be a part on this robot here that tells it to shut down if heat reaches a certain level. We are just going to drill down to something as simple as telling the weather or telling the temperature. So let's talk about microcontrollers and sensors real quick. A microcontroller is an integrated circuit that is designed to kind of be the boss of the applesauce. They say what to do with the information when information is given. So it'll take an input, it'll do some thinking about it, and then it will give you an output. The sensor is the device that's responsible for gathering that input by detecting physical environment elements, and it communicates with the microcontroller to either record this information, simply display it on like another like board or a screen or something like that. And the sensor would also actively be interacting with those elements to collect this information. So, for example, if you wanted to build a auto plant waterer, you would need some part of the sensor that you're going to put down into the dirt to detect how dry the dirt is, for example. So I touched on this a little bit earlier. The Raspberry Pi Pico is a unique microcontroller in that it comes with a sensor on the board, and it's a temperature sensor. Normally, if you wanted to even do something as simple as program a temperature sensor, you would be wiring a microcontroller into the pins. And I just heard a notification sound go off, so I'm going to turn that off real quick. Sorry about that. I don't always hear it, but I know that's going to drive someone insane. Okay. All right, so we're back at it. Normally you would need to wire a sensor to the microcontroller either by soldering it together with cables, or you can use a breadboard to create like a temporary circuit that connects the sensor to the microcontroller, as seen on the right here. So even when you get it all configured, let's say you went the breadboard route and you plugged the sensor into the microcontroller, what happens when you turn it on? Usually nothing. You haven't told the microcontroller what to do with the information that's coming in on that sensor. And to modify this, we are going to need to put some programming onto the microcontroller. It's very similar to writing a program for a normal computer, except for you're working with far fewer resources than you would a laptop or a desktop. We're talking kilobytes or even bytes of memory that you are setting aside for a very specific purpose. So when you go into programming and scripting the microcontroller, you always want to think simple. You don't want to reinvent the wheel. So you're likely going to take advantage of efficient, bite-sized code that other people have written in the form of libraries. That way, if you need something to happen over a span of time, you're not telling the microcontroller, all right, wait 5 seconds. Never mind, I have to tell you what a second is, and then you tell it, how many clock cycles equals a second. Instead of reinventing the wheel every time you need your microcontroller to do something very simple, you can use code that other people have written to kind of cover half the functionality. The other half you will still need to define yourself. And finally, we want to keep in mind that the purpose of this script or this program is that we want to take values in from our environment through that sensor. And these values are typically going to be in the form of yes or no questions or in the form of numerical values, or maybe numerical values that turn into yes or no questions, true or false statements. In the event of a temperature sensor, we specifically want to take the heat that the Raspberry Pi Pico is experiencing and convert that to a number that we can understand, such as Celsius or Fahrenheit. We're going to start by programming the Raspberry Pi Pico to understand its own temperature in Celsius. So I'm going to stop for a moment. If any of you are following along at home, this is the time to get your materials ready. To program a Raspberry Pi Pico, the one thing that I forgot on this slide is that you obviously need some kind of computer. If you have a Raspberry Pi 3B or better with Raspbian installed, that's a perfectly fine computer for this. Otherwise, you can use your laptop, your desktop, anything like that. You're obviously going to need the Raspberry Pi Pico itself. I have my microcontroller right here. And you're going to need a cable to connect that Raspberry Pi Pico to your computer. This is how you send the code to the microcontroller. And on your device, if it's a Raspberry Pi, this is already installed. If you're just using your laptop like I am, you're going to want to download the Thonny IDE, that is Thonny. And this is a integrated development environment that is pretty bare bones, and it's just for writing code that we're going to send to the microcontroller. It also has a lot of support for the libraries that we're going to be using. By default, the Raspberry Pi Pico supports the MicroPython interpreted language, and why that's a good thing in my opinion is normally these microcontrollers like the Arduino, you're going to be using the C programming language or a very similar variant, and the error messages that C gives out as a language are kind of difficult to understand. So it makes troubleshooting more difficult. If you're working in Python, you may get more verbose error messages. You may have an easier time troubleshooting. As long as you don't forget a tab here and there, it's going to look syntactically clean. If you've never written in a programming language in your life, none of this really matters to you right now. Um, I just recommend that you follow along and ask any questions that you have. So we're gonna look at the code here. Before we even get started, let's take a look at the code. Like I said, the Raspberry Pi Pico, it understands MicroPython just at a glance. It doesn't need any extra help. It doesn't need any more steps. That's because there is an onboard interpreter. There is firmware on the microcontroller that is responsible for taking in this human understandable code and converting it into machine code that the microcontroller can understand. And that link there, that bit.ly link, if you're following along, type that in as you see it, lowercase and all, because it is case sensitive, and that will take you to the page that I got this code from. So let's look at it line by line. And if you've never programmed anything before, this part will be very helpful in understanding other projects down the road, as this is kind of it's very similar structure to some of the other projects you would find if you look at code other people have written. So at the top of the file here, we have two lines. They're both import lines. And this is what I was talking about earlier, where we want to import libraries. And libraries are just collections of code that other people have written that kind of define very basic items, very basic understandings. Import machine is a MicroPython specific library that is more so about the machine understanding itself. Our machine in this case is the Raspberry Pi Pico, and it will be able to tell just from the code what a port is, what the sensor is the reset button that's on this board. Is that reset button being clicked? All of these functions have been defined in this machine library, so we're going to hang on to that for a bit. We also imported time. Time is very important because whereas we view the world in seconds, minutes, and hours, the Raspberry Pi Pico, for the very limited time that it's plugged in, it views time as clock cycles. How fast can the CPU form a thought? Well, I can tell you it takes less than a second, sometimes less than a nanosecond, and that is just too fast for us to receive and understand information. So we're going to need the time library to tell the Raspberry Pi Pico, hold on a second, because without that, when it goes to output information, it's going to output it near constantly, which is not very helpful for what we're going to be doing. So that's the first part of the code here. The second part here, we have we're defining important variables within the machine. These are variables that the Raspberry Pi Pico are going to remember and store information in for as long as the program is running. Sensor temp is a value that we want to take in from port 4 or pin 4. All that matters is when we say machine.adc, we are referring to a specific section of the microcontroller that is receiving information. Machine.adc4 is specifically referring to the temperature gauge, or rather the temperature sensor that is on the microcontroller. The next variable that we define here is conversion factor. This temperature sensor reads temperature in a different way. It doesn't read it in degrees like Celsius or Fahrenheit like we do. It reads it in degrees that are quicker to understand from a computer's standpoint. And that's no good for us. If we ask it how hot it is and it says 7,565, well, that doesn't mean anything to me. So we need to convert that to a measurement unit that we use. Drink. So the last part, let's look at this last part here. This is the meat of the sandwich. This is kind of everything has been set up. Let's actually write the program now. And this bottom part is a while true statement, which means when this program turns on, do these 4 things into infinity. Because we kind of flip this switch on, we have no way of turning it off without unplugging the machine. So it's going to continue to run into perpetuum. That is what while true means. It means while this machine is on and while it is running, do these things forever. So let's look at what these things are. The first thing is a local variable called reading. And what this is doing is it's taking the temperature that is being read in from sensor temp and it's converting it to Celsius, or rather it's converting it to a factor that we are familiar with. Temperature is doing the same exact thing. It's another layer of conversion. It is taking that value and converting it into a value that can be displayed on our console. The third line is actually printing that value to the console. And it looks a little strange. Normally you would just put print temperature and then add this variable to the end of it. But they've added some string manipulation, some string comprehension here, where the dot format is inputting whatever the value of temperature is inside those kind of curly brackets. So it looks a little out of turn, but that's just because they are using the output function, or they're using the format function from the string comprehensions library. And then the last part is we're going to tell it to hold on for 2 milliseconds or seconds. I'm not really sure what time is measured in. I think that's 2 milliseconds. And that last line is important because we want to tell it to take a breather and wait. Because if we didn't tell it to wait, it would just keep reading temperature from now until a fraction of a second from now. And then it would do this over and over and over and give us information that only changes ever so slightly. By telling it to wait, we're given information in 2-second or 2 millisecond chunk intervals. So in the 2 milliseconds since you last checked, how hot is the sensor? That's what's being asked here. That's what this entire snippet of code is doing. And this is all we need. So I'm going to back out of this presentation, open up Thony, and kind of give you a live demonstration. So I have already worked on this code a little bit. This was actually one of the first projects I did with the Raspberry Pi Pico. And it was a project that I shamelessly stole out of the book that comes with the Raspberry Pi Pico because it's a good one. You don't need to plug your board into a breadboard or anything. You don't need any extra cables. You just need a micro USB and a Raspberry Pi Pico. And I'm going to plug those in now. There we are. And now that we're plugged in, we can see at the bottom here that the interpreter that we are using is MicroPython for the Raspberry Pi Pico. One other thing that we want to check before we get started is we need to make sure it has found the right board, the right port. This is only relevant if you have multiple microcontrollers plugged into your computer, or if your computer is struggling to find that microcontroller. So what we're going to do is we're going to tell it, hey, look on this COM, and COM is just the USB port. Look here, and you'll know it has found it when you look down in the shell here, and it says the firmware that's on the board and the name of the board. This is super helpful because if you are working with different components that have different library support, you may have to flash your Raspberry Pi Pico to support like CircuitPython, for example, which is like MicroPython, but a different dialect of it. It has different library support, so on and so forth. Assuming that you just bought your Raspberry Pi Pico from like Micro Center, it's going to come with MicroPython on it. So that's what we're going to be using for this example. Let's go ahead and look at our code here. So we've got import machine, import utime. So those are our libraries that we need for this, for the magic to happen. Here we are checking the temp sensor. And here we are defining our conversion value. And those are two kind of global variables that we're going to use throughout the script. And let's go down to this while true statement. And as we said before, while true is while this program is running, do this into infinity. The next line is we are defining the raw value of what's being read from that sensor that we defined up here in line 4. So we are going to define value from temp sensor. And the next line is we are going to convert value from temp sensor to Celsius. And we're going to ignore these two lines for now. Next one is print. We are going to send converted value from memory to the display. In this case, we don't have a display, so we're going to be using the shell at the bottom. And the last step is hold on a minute, because if you don't tell your program to hold on a minute, it's going to go a mile a minute. So now that we've written our code, everything looks well defined, we are going to run it. So up here, if you press F5, it will push the code from your shell through the cable to the Raspberry Pi Pico. So I'm going to go ahead and click that. And we can see it is already running. And every 2 milliseconds, it is checking the room temperature in Celsius. I'm sorry, it's checking the room temperature in its raw value, converting that raw value to Celsius, and then displaying it. And one thing that I like to do, it might not work too well because I have kind of a bad cable here. Like I think it just froze. Oh, let's try that again. Yep, there it goes. All right, so select interpreter. Try to detect automatically. Run. Okay. What I'm going to try to do is I'm going to put my finger on top of the sensor. And as you know, as people, we are very warm. I'm going to put my finger on the sensor, and we should see an increase in temperature. assuming I didn't just bump the cable again. Oh, this is not great for a live performance. All right, so we're gonna restart the program one more time. If I can't get it to work this time, I'll just describe it to you or something. I don't know. But I think we can all imagine what's supposed to happen here. I put my finger on the board. My finger is very warm. The temperature should increase. And it looks like it has already increased considerably from the point that I started fiddling with it. Because if you recall, it was reading about 22 degrees Celsius. It is now, it went all the way up to 26. So it's working. It's able to detect temperature. So let's go ahead and stop this code. And let's go back to our presentation. So we've ran the code. We know that it works, and we even documented it a little bit more. So what's the next step? The next step is recognizing problematic behavior. This is also known as troubleshooting or debugging. If you followed along and the code that you wrote didn't quite work, you may be given an error message defining which line the code got confused on, or the microcontroller got confused on. Look at that line and make sure it's syntactically correct. Did you remember to put a closing parenthesis somewhere? It could be that simple. If you run the code and there are no errors, but it's not doing what you're supposed to, like let's say it was reading 0.00 for some reason, then that is a sign that you need to go back into your definitions and redefine some things. Is it listening to the right device on the port, for example? Let's say nothing went wrong. In our case, just aside from me messing up the cable, it went perfectly. So what's the next step? The next step is improvement. We need to take a look at what we got, pat ourselves on the back, and just start thinking about what we can add on to it to make it better. If you followed this, look at the code again. All right, so this is the part where we're going to look at our code again, and we are going to convert those Celsius values to Fahrenheit, because unless you are a scientist over here in America, we check the temperature with Fahrenheit. So that may make a little bit more sense to us. Oops, too far. So we're going to go back into our code, and I'm going to show you the 2 lines that you need to add, or rather the 1 line that you need to add. In the while true statement, after you have converted the raw value to Celsius, take that value and convert it to Fahrenheit. You can do this by taking whatever the current value is, which is temperature, multiplying it by 1.8, and this needs to be done before you do the addition. So I put parentheses in here to make sure that happens. We should all remember our order of operations: parentheses, multiplication, and then addition. After this line here, and we're going to run the code to find out, we should see a different value come up. And you can see that it's now checking the temperature in degrees Fahrenheit. The board is currently 75 degrees, which makes sense. It's about 75 degrees in my apartment. So what this means is that if I can put my finger on the board, we should see an increase in temperature. There it goes. It just went from 74 degrees Fahrenheit to 76. So the code still works, and it's converted to Fahrenheit. Awesome. Slide. That was everything I had for the day 1 workshop for Digital Inclusion Week. This was Introduction to Robotics, Microcontrollers and Sensors using the Raspberry Pi Pico. If you followed along and you were able to make it this far, you got it to read the temperature correctly, congratulations. If you're watching this after the fact as an archived video and you want to try this, I highly recommend you go check out your local Micro Center or just order this thing online. It's about $4, $6 or $10 if you get a cable with it to plug it in. because when you buy the microcontroller, it won't even have pins in it. It'll just be a naked board with empty holes along the side, no cable included. So if you want to follow along to this, you at least need to make sure you have a micro USB controller and rewind the video and give it a shot. If you have any questions, you can reach me at anthony@oakhillcollaborative.org. I will also be doing a short write-up of this experiment. It's really just kind of a duplicate of what I found in the Get Starting book. So if you have that already, I don't recommend seeing what I have to say about it because it's the same thing. So let's just go over some commonly asked questions while I wait for questions to enter the chat, if there are any. Is the Raspberry Pi Pico a robot? I would think of it less as a robot and more as a single component of a robot, because you got to remember that robots are a system of components working together to reach a certain function. So, is it a robot? Is a temperature gauge a robot? I don't know. I think it is more of a component. What can I do to get more into robotics? So if you liked what you saw here, but felt you wanted to do a little bit more, first I recommend coming to our, what was it, third or fourth? I think it's our fourth Digital Inclusion Week talk. That's going to be this Wednesday at 6 p.m. Cameron Hughes from C-Test Labs is going to be taking basically what I talked about here today to a new level. So that's a great place to start. If you just want more general advice, say you can't make it to that workshop, I would say look for a problem that you want to solve using technology. Even if it's something as simple as stirring your coffee, find a way to hook up motors and sensors and microcontrollers that spin a spoon in a circle, and huzzah, you've built a coffee stirring robot. Now, that's always easier said than done, so I recommend that if you like that idea, take it and run with it, because I will certainly not be using it. So that's all for Q&A. Let's go ahead and check our live chat. Looks like no questions in live chat. That's fine. Just one more time, if you want to reach out with questions after the fact, you can reach me at anthony@oakhillcollaborative.org. Thank you all for attending Digital Inclusion Week, Day 1. This has been robotics at a tiny scale with the Raspberry Pi Pico. I think that's all. So I'm going to go ahead and hop off. Thank you. And be sure to check out the other talks.